All right, so y'all enjoy your Labor Day weekend? Now back to torture. So starting this week, class is going to be a tad different. On Tuesdays, it's going to be the normal lecture like we're doing, and on Thursdays, you are not permitted to leave. Sure. No, you have to hold it. This is the military. So we're going to do normal lecture on Tuesday. And then on Thursday, what we're going to be doing is we're going to be doing the ILS course, where I'm going to provide a little bit of supplemental lecture at the beginning. We're going to start doing Verilog. And then, so the first little bit, I'm going to go over, I'm going to show you what the TGOs are that I want you to do. And then the rest of the class and over the weekend are going to be the topical guide objectives and brief lab exercises from the actual course. In the past, I've kind of put it all towards the end of the semester, and when everybody else is putting everything else at the end of the semester like that, it tends to put a lot of stress on the students. And I've also found that being able to simultaneously code concepts like, you just went over full adders in the last couple of lectures. So you're actually going to be coding up a full adder in Verilog, and coding up multiplexers, you're going to be coding up comparator circuits, and you're eventually going to be building up, today we're going to start talking about memory elements. So you're actually going to be coding and reinforcing the learning that you're doing in the data path design. And so I'm hoping that before you guys get through midterms, we'll be through the full Verilog portion of the course. By the end of the Verilog class, you'll have actually built your own, you'll have designed and simulated your own central processing unit. And usually when students get to that, they get really excited because they can see the whole CPU working, and it's a pretty cool thing. And then towards the end of the semester, we'll go through a specific type of processor called Tensilica, where basically it's a bit reconfigurable. You can actually use the tool to actually design your own advanced digital system. So that's how we're going to be doing this. So at the last 5 minutes of lecture today, what I'm going to give you is the opportunity to briefly meet up with your groups. I sent out the email yesterday indicating which who your group members are, and odds are good so many of you don't know at least one or two people in your group, if not more. So what I'm going to do is I'm going to put the actual lists up, and then I'm going to try to help you guys find each other. So, all right, so up to this point, we've learned what performance is, fundamental of what an advanced digital system is. We've talked about arithmetic logic units. And so up to this point, I've been talking about this ubiquitous concept of register, and you've kind of seen me allude to it. S3, for example, you have some $sign. What that is when we're going to start getting into coding, and you're going to be learning Verilog, just enough C to be able to understand what's going on in the digital system, and MIPS, which is an assembly language. And so this is specifically the assembly language that indicates which register I want. And so if you remember earlier in the course, I talked about this idea that data can be only operated on in a register or a load store from instructions from accessing the memory. Well, the memory tends to take longer to access than these really fast registers. And so the whole idea is that using these registers speeds up performance. And so today we're actually going to learn how that's done. And so how we want to start this out, first let's formally define what a register actually is, if this actually ever scrolls up. Registers store bits of information in such a way that systems can write to or read out all of the bits simultaneously. So the bus that reads in and reads out from the registers in MIPS is 32 bits. And so what we do is we have a read signal or a write signal. If it's a read signal, it puts the value on the output, and then we use a multiplexer to determine which registers we actually want to get. And if it's a write signal, we have a register write, and then the 5-bit value that's coming from all that RS, I kind of briefly alluded to it, but we'll formally define it here in a moment, about that 5-bit value that comes from the instruction. That tells me that's actually used in multiplexers to determine which register I want to write to. Right, so let me scroll up. This computer is struggle busting a bit today, but better than having like the old transparencies like that back in the day, right? All right, so there are several types of instruction fields that can happen, and there's 3 types of instruction formats. So first I want to go over all of the different types of instruction formats, and then down here we're actually going to go over what those 3 formats are. In fact, I'm going to scroll past register so we can see both of them kind of simultaneously. The opcode is the first 6 bits of any instruction, and it defines the basic operation of that instruction. So if you all look on the MIP screen sheet, you'll actually see that in all R-types instructions, the first 6 bits are 0. Right? And so what is an R-type instruction? It's actually defined as a register instruction. And that means used for instructions that perform an operation on 2 registers and then store a result in a third register. So in order to find what those 3 registers are, we have RS, RT, and RD. So RS is the first register source operand, RT is the second register source operand, and RD is the destination operand. In R-type instructions, there's a very specific value here. And so as you can see here, all those are 5 bits, and the reason why is 2 to the 5 is equal to 32. So this allows us to say if this is like 18, I want the 18th register. And on the MIP screen sheet, and I'll show you, I've got some stuff in the slides here that indicate which register number correlates to which value. The shift amount is also 5 bits, and the reason why is I can't shift by any more than the number of bits that I actually have. So I can shift between 1 and 32 bits, and oftentimes that's used for multiplication and division. So if I want to specifically for multiples of 2. So if I want to multiply by 4, that's going to become really important later in the course, I shift left by 2. So think of it this way, that's 3, and if I add 2 zeros, base 2, that becomes 12. So if I want to shift left by 2, then this value is just 2. The last 6 bits of an R-type instruction are known as the function. We've kind of gone over that a little bit when we were talking about ALU design. Formally defined, it selects the specific variant on the opcode. So in R-type instructions, the opcode is always 0, and then we learn specifically about addition and subtraction, where that 1 bit that allows us to differentiate between the addition and subtraction will come from the function. And that function, if you remember from the previous section, goes to the ALU operation, the ALU controller, and then performs that logic, and then that 4-bit output that goes to the arithmetic logic unit. And that was what you learned in the previous TGO in the previous section. So then we have 2 other types of operands that can be used for what are known as I-type and J-type instructions. So I'm going to scroll down a little bit past RD, right? So you can see the full TGO 3.3 here. First, in 3.2, we're talking about integer. Is a 16-bit value indicating an immediate or integer value. So in this specific case, it's the last 16 bits of an I-type instruction. Okay. So here you see that the last 16 bits here are RD, shift amount, and the function, right? So I somehow need to be able to differentiate these 2. First, that starts out with the opcode, which goes to a controller. That controller generates a signal, which I then use for, and what was the device that I can have a select signal, 2 inputs, and I select between the 2 of them? Yes, multiplexer, right? So then you have a mux here. And so we'll learn about what those control signals are and how many muxes, all that. We'll learn that later. So, but the key thing is, what you need to understand at this given moment is that the opcode allows us to say whether or not those last 16 bits are either tell me any total register, shift amount, and function, or is it just a 16-bit number? And so for I-types, used for data transfer instructions, I can use those for one of two things. I'm either like doing addition, where I'm adding C equals A plus 5, or I can do what's known as a load word or a store word instruction. We'll go into that in more detail, but this allows me to figure out what the offset on the pointer is. So I'm going to explain to you physically what a pointer is. We'll do that today. And then I'm going to explain to you how that ties. You all have done arrays, right? I know some of you have coded in Java and didn't do much with pointers. It's okay. I will explain. But the key thing is a pointer basically tells me where the element in memory starts. And then the offset tells me, so if I have A of 4, right? This tells me how many blocks I need to go down. So have I told you guys that MIPS is byte addressing? Have I? Oh no, this is lecture. We're in memory, so I haven't said that to you yet. Anyway, I want to overload you. So for right now, there is a number there, and I'll teach you how to calculate that number based off of A of 4. It's going to be 16. So I go 16 bytes, and that tells me where specifically A of 4 is. And then RS contains the location of the initial pointer in that specific case. We'll go over all that in more detail, so I don't want you to feel overwhelmed. Lastly, in 3.2, jump indicates the jump address. And in this specific case, we use 26 bits to indicate where it's going to be. And then I'm going to teach you I'm also going to teach you today how we take this 26-bit value and turn it into a 32-bit value. Okay, so does anybody have any questions on this so far? So 3.4, I have found in the past that students tend to get confused by RS, RT, and RD, so I want to reiterate it a little more clearly here. RS is a source register for all R-type and I-type instructions, right? So RS is going to tell me where I need to get something to perform an operation on. RT is a source register for all R-type instructions and a destination register for I-type instructions. So if I have an RT, basically what this means is, to give you that example, C equals A plus 5. A typical type of question will be, I assume that S0 is A and S1 is C. That means S0 is going to be RS, S1 is going to be RT, and what's going to happen is I'm going to take the number in S0, add 5, and then store it in S1. And here in the MIPS screen sheet, they define it as RT. And then RD is the destination register for all R-type instructions. Let me scroll up a little bit here so you guys can see that previous TGO a little more. Okay, so what I want to do next is I want to talk to you about what these registers actually are. So this specific TGO directly comes from the MIPS screen sheet, and if we actually fully scroll up here, I want to get all the way to the 32 bits. All right, good. All right, so I want to go over each of these specific registers. So MIPS has 32 registers. Makes sense because we have 2 to the 5, 32, and this is what each register actually does. So we have a name for them. The name is what's in the assembly language. So when we're going to be writing assembly language, we're going to actually discuss, this is what's actually used in there. The number is what actually correlates in the physical 5-bit value. So for example, if I say S1, right? I go here and I see that S0 through S7 correlates to 16. That means S1 correlates to 17. So let's go here. First, this $0 is a register that contains the number 0. and may never be written over. And what you're gonna, when we start getting into more details about how these instructions actually work, you're gonna find that having a register that contains 0 becomes tremendously useful. Saves you a lot of time and extra. You don't have to do a lot of shifting. You can basically just use this specific. If it's, for example, if you need to compare something that's greater than 0, you just use this 0 bit instead of having to store a value 0 into a specific temporary register, and saves you a couple clock cycles, which become very important when we do performance improvement. So next, and we're not really going to use the assembler temporary in this course, but that is specifically for what happens when we are compiling and we need to have a specific register that we store values in. Right? What we're going to be doing in this course, since we're focusing primarily on compiler-driven encoding of the microengine to reinforce the advanced digital system concept, is we're going to be talking about how do we actually manipulate the rest of these to be able to improve the computing performance. So if you've ever written a function, you know, if you've had int foo, right, and then you have integer bar, right, and then it does something and then return in some sort of integer, right? So what's actually happening there? I have, what's happening is the same data path is performing the function, and then I save a specific register to return the value that the function is actually going to do, right? So this returns it there. What's happening is I can have 2 potential values in the event that I need to use I need to do functions back to back. So I have 2 registers, V0 and V1, that the numbers are 2 and 3, and they're values for function results and expression evaluation. So I need to, let's say I need to store a result of an expression. Is that true? If I need to store that, I can use one of these 2 as well. A0 through A3 are function arguments. So in that previous thing that I had up here, where I had it returns an integer foo, I'll get to your question in a second. And then in bar, what I'm going to actually be doing is I pass these values in these specific registers. Okay? So, for those of you who've taken C++, you know how you write you have pass by value and pass by reference, and when you do if you pass by value, the things that change in the function aren't overwritten. It can't be overwritten. Once the function's done, you lose that specific value, and it reverts to the normal value. The reason why is, let's say I have I equals 4, and then I call foo of I, right? So I'm passing by value here. And then I say printf I, right? I don't know. So basically, I'm printing it to the screen. Whatever happens to I in the foo function doesn't change, unless I'm passing it by reference, which we'll get to later in this course. But what you need to know now is what I'm going to do is I'm going to store one of these saved temporaries, which is where I is going to be saved, and I am going to store it in one of these arguments, so that all of the changes physically happen differently in this specific register A0 through A3. I perform all of these operations, and then I return some value in V0, right? So let's say I had J equals foo of I. It returns the value, stores in another saved temporary, and all the changes that happen to I inside that function are happening in this physical register. However, when I have I equals 4, it's these registers when it's not in the function. That's physically why when you pass by value and you go back up to the main function instead of this other function foo, That's why all the changes disappear if you're passing by value. Okay. So we have 3 specific registers where we're passing function arguments. Now, here we actually have 8 saved temporaries, right? The saved temporaries are what's saved in the registers and we use for variables. We actually have more registers, 8 through 15, and then 24 and 25, which are just temporary values. They don't actually have a variable assigned to them. And as we get into load and store operations and other types of addition, we'll see why they're important. But let me give you an example. A equals B plus C plus D, right? Because we are using a RISC architecture, and so this is a good difference between RISC and CISC. In CISC, I could actually design an arithmetic logic unit that will add 3 if that's a common operation. In this RISC architecture, I need to add B and C, store that result, and then that result has D added to it. Now, a common student mistake is they go A equals B plus C, and then they go A equals A plus D. What's wrong with that? Any ideas? Right, and that secondary variable is temporaries. But why should we? So what is specifically wrong with that?
You're changing your initial variable. You're messing with something. You need to pass it to another variable and change that.
But even simpler, you are correct. I'm trying to get even to a more simpler concept. The coder didn't write A equals A B plus C, right? You have to deliver what the coder asks for. So in this specific case, what you're saying is you have to be able to create a temporary value because the coder didn't say. So if I were to say A equals B plus C, the coder never said that. Therefore, the value of A is wrong and does not represent what the coder gave you in the compiler. Therefore, what we're actually going to do, let's say T0 is my temporary. What I would say is T0 is equal to B plus C, and then I would say A equals T0 plus D. Difference between computer architecture and computer organization. Temporary registers are a physical detail that are transparent to the coder. Transparent to the programmer. Programmer, coder, same difference, right? But you can't manipulate that. That's done with the compiler. You know that they're there, but you can't actually write that code. So it's there to help you. And then the saved temporary are the ones that we actually use for the registers. 26 and 7 are reserved for the OS kernel, K0 and K1. And when we get to exceptions and interrupts, this is where we're going to really worry about 26 and 27. Right? What that basically does is when I say I either have some sort of overflow where I can no longer guarantee the correct operation of the instruction, or for some reason the compiler generates an opcode that the data path doesn't have because it's not part of the instruction set. What we do is we go, hey, something's wrong, and then I'm going to store the program counter into the OS kernel. Now there's 2 specific ones because I have one for exception and one for interrupt. Exception, interrupt. If I have a specific thing, I store the program counter there, and then it sends it off to the operating system kernel. If you want to learn about all that, you can take Computer Science Operating Systems course where there's whole kinds of different algorithms for how the kernel takes care of that. For those of you who don't know what I'm talking about, the kernel, and we're not going to define it in this course, but the kernel is the portion of the operating system that cannot be manipulated with any programming. It's specifically protected to ensure that's maintaining the proper operation. So the OS kernel, if you need to deal with the operating system kernel, that means that all of the other things that you've done physically in the physical details in the architecture or in the compiler or in the software that you've written, all of those protections have failed, right? All of those try-catch blocks, all the exceptions. Now we're dealing with the OS kernel. That means something went really wrong. And then here, if you're basically familiar, we're not going. This is another thing that we're not really going to deal with that much: global pointer, stack pointer, and frame pointer. But basically, in the memory, I need to maintain a certain amount of memory for a program, right? Again, how that's actually done with segmentation is an operating systems course problem. It's a little outside the scope of this class. But the operating system does some magic. And then it says, all right, I need to define where the program starts, and I need to define, when I do you're all familiar with recursion, right? So you're familiar that when you're doing recursion, you have different stacks. Right? So if I'm in a different particular stack, my stack pointer indicates what I'm actually doing, right? Whereas the frame pointer indicates the specific frame where the portion of the program that I am performing at that given moment is running. And then global pointer tells me where the whole program is. And that's all you're ever going to need to know about that. So those things are done by the operating system. The last thing is return address. So the return address, remember that I have a function I can pass. This is the result. These are the function inputs, right? So I do some stuff in the physical instruction memory, right? I conduct a number in this function, and then the actual main function is located in another thing. So the return address says when I get here, I need to jump back here. And what that means is I have I equals 5, j equals foo of I, and then k equals I plus j, right? So what this return address is doing, I jump to the portion of the instruction memory that contains the function. It does the function stuff, and then the return address tells me I need to jump back here in the instruction memory so I can begin again in the main function. Okay, so does anybody have any questions about that? I hope I was clear in what's inside and outside the scope of the class. Okay. So again, I showed you this a little bit. If this is available on Blackboard, the MIP screen sheet under supplementary materials. But when we're looking at this, we have operation in Verilog. Right? And so the what this means is the register value that's stored in RS, right? That's what the notation means, plus the register value that's stored in RT is equal to the value that's going to be stored in RD, right? And so if you remember from opcode, it's going to be 0, so it's 6 zeros. 20 hex means it's 10 and then 0000 in binary, right? That's 2 hex. Normally, if you're representing 2 hexadecimal numbers, you would need 8 bits, but because we only have 6 bits, you're not going to get anything that goes over 2 or 3 there. Because you have this value that has 4 digits, and then you have here the largest value you can represent is 1, 1. So it's going to be 0, 1, 2, or 3. And so that's how you read that portion of the MIPS green sheet. Another thing that came off the MIPS green sheet, this is straight from the green sheet here as well. And also, if I can scroll up a little further, I took these off of the MIPS green sheet and then came up with definitions to define them. So what I'm trying to do, and this is what's important, how are you going to use this beyond my class, right? That's ultimately what you want to know. You may never deal with this particular data path again. But one thing that I constantly hear from employers is that students have no idea how to read the technical documents. So what we're doing is I've provided you a technical document and I'm breaking it down to show you how you actually should be able to read it. So that way when you get into industry, what you can do is you can go through your own technical, oh, that's what that means, I can look this up. So that's the skill that you'll be able to take beyond this specific course. And then I've also noted that on the exam or quiz, I will provide the MIP screen sheet for you. All right, so this byte addressing that I was alluding to earlier. All right, byte addressing means that an index points to a byte, 8 bits of memory. So what does that mean? When I want to swap in blocks, and we're going to talk about blocks and everything like this later, but let's say I have a block of memory, and we use 32 bits to represent a word. 32 bits is something that I would be loading into memory, loading from memory into the data path and storing back into memory, right? What byte addressing means is that I break them down into 4 bytes, 4 8-bit bytes. So let's say I'm doing this load word instruction that I was telling you about before. So load word, so this is an example of a load word. Let's say 8S1, right? So what does that instruction mean? And this is something that comes off of the MIP screen sheet again. I take, also load word is an I-type instruction since it's a data transfer instruction. I take S1, which is the index. I have this block. S1 tells me that this array, I should really pick anywhere else but where I drew it. This array starts here. That pointer is S1. That's what a pointer physically is, right? Now, a second pointer is, this is actually getting something from memory. So my second pointer that's created here, and when we get to the actual assembly language, you're going to see what's physically going on here. I get an offset. And so I am going down 8 bytes. Right? So 0, if it's 0, I just start there and grab the next 4. So if it's byte addressing, I grab 4 bytes to create the 32-bit value that I need. Does that make sense? So this would be 0, 1, 2, 3. 4, 5, 6, 7, and then the 8th one is down here, right? So I add 8, I start at 8. The number that's going to be in here is going to be some multiple of 4. So if I'm getting a 0, that means I'm going straight to, this means that the array A is in S1, that's my index, and then 0 grabs me 0, 1, 2, and 3 because we're using this byte addressing. If it's A1, that means I'm grabbing 4, 5, 6, and 7. If that means it's 8, that means I'm grabbing A2. So if I'm grabbing A7, what are the 4 bytes that I'm grabbing? What's that?
0 through 3.
No, 0 through 3 if I'm doing A0. So let's do some pattern here. So if I'm doing 0 through 3 and then A1's 4 through 7, and then 4 through 7, and then 8, 9, 10, and 11 is A2. What is A7? No. There we go, 28 through 31. Right? 8 times 0 is 0, 1, 2, and 3. 1 is 4, 5, 6, and 7. A2 is 8, 9, 10, and 11. Yeah, there. Yep. That's why I let you guys, sometimes I let you guys struggle with it, because eventually you think through it, why is that wrong? And that helps reinforce the concept. Because I've seen this just thrown out when I took the class, and then it was a bloodbath on the exam. Y'all don't want that, right? Y'all want good grades. So let's discuss it the right way. So A11, which 4 are they? Yes, 44, 45, 46, and 47. So if I'm going back to, if I have load word S3 and 32 S1, what that means with this concept of byte addressing, it's going to be 32 divided by 4, which it means I have A of 8. Does that make sense? So if I had A of 8, you multiply that by 4, that gives you the initial byte in this byte addressing concept. And then you do 32, 33, 34, and 35. And that is what is loaded into a register. So that's what a pointer physically is. A pointer indicates where the address is in the data memory. So the pointer actually is a physical value. And then an array tells me, I know where the initial physical value is, and the array just tells me the offset. And then how do I determine the offset? I have to know the specific type of addressing. So if it's word addressing, then A of 3 would just have an offset of 3 because its word is 32 bits. Does that make sense? Cool. So MIP specifically uses something called byte addressing. So 3.7, and I know this is a long one, but I think this is really important because this covers all of the different types of memory addressing. And as you can tell, I consider that really important. So all the different types of memory addressing in an advanced digital system. Immediate. So in this specific case, the operand is a constant within the instruction itself, right? So I've been talking about this load word and store word operation. The instruction memory actually tells me what it actually is. It's stored there. The value of, so if I have, in order to calculate 32, I know it's A of 8. So the number that's actually going to be there is 8 times 4, 32, and that's what's stored in instruction memory. So that's its own form of memory. The second one is register addressing. So register addressing, I've alluded to this a lot with RS, RT, and RD. But how do we actually get that? So what happens is I take the instruction, I go through, it's a 5-bit value, and it goes through a 5 to 32 decoder. Now, does anybody here know what I mean by that? 5 to 32 decoder. All right, so a 5 to 32-bit decoder is this. I put in a 5-bit value, and it basically, through a series of AND gates and inverters, will actually have a 32 bits on the output, and based on the logic, like let's say this is 7, right? So it's 0, 0, 4, 6, 7, right? So that's the 5-bit value there. That means all of these are going to be zeros except for the 7th output is a 1, and all the rest are zeros, right? So that's what's known as a decoder. So if that's a decoder, what's an encoder? Opposite. Bingo. Exactly right. I saw a bunch of hands go up. So you would have a 32 to 5 encoder, which would say based on whichever one of these is on, you should be able to produce a binary number representation. So where you have this, for example, is that you have a certain value that comes into your cable box, and you're constantly rotating through on which one you want. If you say you want HBO or ESPN or whether, insert your favorite channel here, you have a specific number you want. So as it's rotating through, what it says is, I want this specific channel. I want Game of Thrones. I want Ole Miss beating Texas Tech, right? And then it goes through, and instead it selects the specific one you want, and that's what shows up on your TV screen. So that's what a 5 to 32-bit decoder is. And what ends up happening is we have, as you just found out, 32 separate registers. And I want to read from a specific one, so only one of them will have a 1. That 1 means I want to read from that, or I want to write to it, right? And it tells me this is the specific register. Make sense? So that's what's known as register addressing. So the operand itself is the register. So the third of the 5 types of addressing are what's known as base addressing. And so base addressing is the formal definition of what I just described to you with load word and store word, right? Here's what's physically going on. Here, I've drawn this all up so you see 15 to 0 there. So this is an immediate type instruction, an I-type instruction. So base addressing we formally define as the operand is at the memory location whose address is the sum of a register and a constant in the instruction. So in this case, it's the immediate, right? So what ends up happening is RS, if we have a load word S0, and then we have 16 S1, right? So if I have 16, just to kind of quiz you guys again, what's the array value in byte addressing? Say it, I hear you. 4, exactly right. So that means so what this means is sum of a register is where the array starts, and then I'm adding this sum to get my specific value that I want. This is known as base addressing. So here's what goes on. I use register addressing. I go to my 5 to 32-bit decoder. I get the value that I want from the register. That was my S0. I send it to the arithmetic logic unit. I get the 16-bit immediate value. In this case, we calculated it was 16, right? And then what I do is I do a sign extension. So now I have a 32-bit value, right? If it's positive, it looks at that most significant bit. If it's 1, it adds all 1s. If it's 0, it adds all 0s. And yes, and sometimes when you get into a more complex addressing, you might want to have a negative number there. Okay? Again, operating systems, you can learn much more about that. But I get a sign extension so I can put 2 32-bit values into the arithmetic logic unit. And what comes out of the ALU is the actual physical location of that specific array element. That 32-bit, later we're going to find out that it's eventually just put back into a register. That's what's known as loading, which is why it's load word, where word is 32 bits. Load word into the registers. Okay. So does that make sense? This, for those of you who are taking C++, that's what a pointer actually is. And for those of you who haven't taken C++ or C, that's what a pointer actually is. It's like I've taken Java, so it's no longer a fact. Right. Okay, so does anybody have any questions before I move on to PC relative and pseudo addressing? Okay, so PC relative, right? The branch address is the sum of the program counter and a constant in the instruction. All right, so I've alluded to branching. We're going to formally define it a little later. But it's if you have I equals j, if you've met the condition, you're doing the instructions inside the if statement. Branching is what happens when I don't want to do it. I want to branch past those. So we have a differentiation between jump, which allows me to go to any address, and branching, which is specifically for if statements. Okay. So here's what's going on here, right? I have PC, I have the program counter, and then I'm adding 4. So why would I want to add 4? If I have a program that's a 32-bit value that tells me the specific instruction I want to use, why would I want to add 4 to that? Yes?
Because you want to go to the end of the four registers.
Byte addressing, bytes, yes. So. Yeah, you're exactly right. So again, just like in data memory, we're using byte addressing. So we're adding 4. If I have an instruction memory that's telling me this is where the instruction is, I add 4, I go to 4 bytes, that's where the next instruction is. So PC plus 4 just says go to the next instruction. Okay? Here, I've moved on one pass instruction here, and I go to an adder. We physically have an adder, it's not the arithmetic logic unit. I then take how many instructions I want to branch past, right? So if I have if I equals j, right? And then let's say for some reason I have four instructions in there that I want to branch past. This becomes 16. So if there's 4 in here, I don't want to just add 4 because then I end up at the last instruction inside the brackets, right? I want to do one more. So I get to the 5th one, which is here. So here I've added one instruction. I have 16, which is 4 instructions. That gets me to the 5th instruction. And instead of going to data memory, and if you look here, you see the difference here between data memory and instruction memory. The instruction memory tells me, all right, I want to go a total of 5 instructions. So this is 16 here. This is 4. So the output is 20 plus PC. So this is PC plus 20. And PC is just a common term for program counter. So the PC is the current instruction, where that would be the if I equals j. I have 4 instructions that are inside there. I don't want to do them. That means I need to branch 5 instructions. So now I am at the 5th instruction. I've managed to get around the if statement. So that's what's known as PC relative, because it's relative to the program counter. And last but certainly not least is pseudo direct. Pseudo direct is what we're using for jumping. Jumping would be I'm at the end of a function, I need to get back to the next instruction, or there's all kinds of different things that you can use. If you're doing while loops, for example, I need to jump to the first instruction in the loop to see if I've met the condition. And then if I don't, I would branch past. Does that make sense? So pseudo direct is how I would do any kind of jump. So what I'm doing is it's a specific type of J type of instruction. I get 26 bits from there, right? I need 32. 26. SL2, that's the abbreviation you're going to see me use a lot for shift left 2. So I'm appending 2 bits to the right of it. So basically I'm multiplying by 4 because byte addressing. So now I have 28 bits. So I still need 32. So what I have is I have my program counter. I've added 4. And this here is what's known, and I'm guessing none of you know what this is, concatenate. Right? What I'm doing is I'm taking the 4 most significant bits of the program counter and I'm concatenating them to the front of the jump address. I'm seeing a lot of confusion. Please feel free to ask questions. Don't be shy. Okay, or you can all be shy. Yes?
With shift left 2, so does that act sort of as a buffer between the original 26-bit function and then the concatenation?
Right. So here, the jump instruction includes the number of instructions I want to jump past. Shift left by 2. So let's say I want to jump like 8, right? Because of byte addressing, that's 32. 16, 32, right? That's where shift left 2 comes from. So I'm still doing the byte addressing. So because of the fact that we have a fixed number of fixed instruction width, I can't. CISC, I would just say, okay, it's a jump type instruction. I would just add the 6 bits there and calculate everything out that way. But because we're limited, because it's a reduced instruction set computer, we have come up with this pseudo direct addressing methodology to be able to calculate a jump address. Any other questions? All right, so let me read it so we can formally define. The jump address is the 26 bits of the instruction concatenated with the 4 most significant bits of the program counter. So we just basically duplicate that value. All right, so those are the 5. Any type you want to access anything in memory in the advanced digital system, you're going to use one of those 5 types of memory addressings. So it's immediate, register, PC relative, pseudo direct, base addressing. And so the question will be state, define, and draw the 5 types of memory addressing. Okay, so here basically what I'm alluding to there is something that I've said several times, is that when we do branching and we do what's known as pipelining, if we have multiple instructions in the pipeline at the same time, we have to worry about making sure. So let's say I have an instruction where I'm calculating the result, right? And so I remember how the pipelining is 5 stages, and it's calculated at the 3rd stage. So if I have if I equals j, right, and this is at the 3rd stage, well, I have instruction fetch and instruction decode of j equals j plus 2 and I equals I plus 4, for example, right? So instruction fetch and instruction decode actually are in the data path. But let's say it's calculated that I want to branch past that. So how do I take care of that? So that's what these issues are, what are known as data hazards, and we'll go into a lot more detail in later sections about something known as branch prediction. The whole idea is I actually, based on previous knowledge of how the program has worked, there's a high probability that the branching will occur in a specific way. Now, it's not guaranteed. What happens if we guess incorrectly? And there's a whole way of doing that. And we'll cover that later in the course. It's actually really neat stuff. But it kind of alludes to the point of when you add higher performance, it tends to come with more challenges. Okay, so define the principle of locality and state and define the 2 types of locality. So I have this big chunk of non-volatile memory, right? And if you look in here and you have your local registers, but eventually when you turn the computer off, it's stored in typically it's known as RAID of inexpensive disks. And the whole idea is that I have to store them somehow, right? Now, I can be inefficient and just store it wherever, right? When you're in your groups on Thursday, for example, it would be incredibly inefficient if I had one group member over here, one group member over there, one group member. It would be really hard for you all to work together, right? So operating systems cluster memory in very much the same way. You want to keep the stuff that's being used together so that way you can access it efficiently. And so the principle of locality is that a program tends to access data that forms a physical cluster in memory. Right? Multiple accesses may be made within the same block. So you guys create your cadence group. All of you, for a group of 3 or 4 sits in the front row, and you asked me 4 different questions. Your group asked me 4 different. So say 3 of you. I think the 3 of you are. So this works. All right. So you guys have 4 questions that you want to ask me, right? So what's going to happen is that the operating system, in this case me, would say, "You have a question." Yes, question. Before I move on, it would be really inefficient if I went back to the group over there, answered their question, and came back here, went back there. That would get really annoying really fast. The more efficient way to do it is I ask you, if you have any questions, you ask your questions, I answer them, and then I follow up. Do you have any other questions before I move on to another group? Once you feel comfortable, then the operating system comes back here, and then I say, "Hey, do you all have any questions?" You say yes, no, and so you want to have the computer and operating system kind of reflect some common sense in this specific case. So multiple accesses may be made within the same block. So each of the group represents a block, right? And so that's done in one of 2 ways: temp, space, and time. So it's like Doctor Who, right? So temporal locality and spatial locality. Temporal locality, if an item is referenced, it will tend to be referenced again soon. Right? And that makes sense. If you're all our program, and I said that I equals j, and then I do something to I, do something to j, odds are very good that Shelby is a variable that we're operating upon in this program. Odds are good if she is part of an instruction, odds are very good very soon I'm going to be doing something else again here, right? It's not like, okay, what's your value? And then I stay away for like half of the program, right? That's not how most of the programs work, right? Same thing. And so that's what's known as temporal locality. If an item is referenced, it will tend to be referenced again soon. And spatial locality, if an item is referenced, items whose memory addresses are close by tend to be referenced soon. So in this specific case, let's say that I ask for your value, right? And then we perform some sort of operation. Odds are good that based on the way that memory is clustered, the variables here are going to be what I'm asking for next. Okay? That's what's known as spatial locality. So temporal locality, I ask, and I'm going to probably ask you again very soon. Space, if I'm asking you, odds are good I'm going to be asking for you then. You see that? Memory acts in very much the same way. So spatial locality is formally defined if an item is referenced, items whose memory addresses are close by will tend to be referenced soon. So a good operating system will do that. And so how do I determine how I cluster those? Well, a specific term, what's known as memory hierarchy. So memory hierarchy is a structure that uses multiple levels of memory in order to improve memory access time. I briefly alluded to this in the first lecture, the idea of local registers, cache memory, then non-volatile memory, where there's trade-offs between those in this diagram that I'm going to show after I scroll up here, and after you all get the memory hierarchy definition, we'll show that. So the trade-off is typically access time versus cost. So usually when I talk about cache memory, well, why don't we make the whole memory cache? Well, because it requires a lot of cache. And so at the bottom here, I'm going to scroll past just the definition of temporal locality. I'll scroll past temporal locality as well. As the distance from the processor increases, the size of memory and access time both increase. So basically what that means is the registers are the fastest access time. And the reason why is because I want to perform a bunch of operations on them as fast as possible. Next is the local data memory, which is your cache memory. So all of you would be my very fast registers, right? Perform an operation, I'm done. And then what ends up happening is you're my first program. If I'm done, I want to do a bunch of load and store, swap to my level 1 cache, and then pull in the second portion of that program, update my global pointer, right? Oh, I'm sorry, my frame pointer. And then if I have to create a different program, I would swap level 1 and level 2 out in cache, and then bring in the things that I want to operate in the registry. So think of it this way. I'm going to operate on you a lot in the registry. You I'm going to operate on every once in a while. And as I get further and further back, I'm going to operate on you less and less, right? Because these memory items cluster. So instead of just having to custom go register, level 3 cache, level 2 cache, I want to be able to cluster them effectively. And so what ends up happening is this main memory, because it's so slow, it can take up to 100 times longer than a typical cache. And so this diagram kind of shows the trade-off here. So here we have the processor, memory. As the memory gets larger, it tends to have a high cost and tends to go. So you have SRAM, static random access memory, dynamic random access memory, and then magnetic disks. Redundant arrays of inexpensive disks, or RAID. So you get the idea? We want to take advantage of these temporal and spatial locality to try to figure out how I can get really high performance while not driving up the cost of the computer. Okay. So does anybody have any questions about temporal locality? All right. And so what is cache memory? Cache memory is formally defined as the level of memory hierarchy between the processor and the main memory, and it's used to take advantage of temporal and spatial locality.
Does RAM typically just run the operating system while the other SSD drive?
Okay, so think of it more like this. The operating system is typically what's kind of controlling the whole computer, right? And you need it to be able to control both the advanced visual system, which in this case we're talking about data path, right? But the data path is going to produce some binary result which we want to do something with, right? So in this specific case, let's use my computer as an example. I have multiple core processors. One of them is processing everything I do with the mouse, right? One of them is processing everything I do with the screen, right? I need a processor to actually take the result from the PDF and put it on the screen so you can see it. I'm also recording everything. So I'm recording all of my movements on the screen plus everything from a microphone that's going into the computer. Additionally, I need to be able to refresh this screen all the time. Additionally, if I type into a keyboard, I need to be able to have it automatically get all of that. So the operating system manages all of those different things. So at any given moment, something needs to have the priority, right? So in this specific case, the computer is constantly refreshing the screen. But if I, try to type in something, let's say I want to, I would just type notepad, right? So the operating system allows me to go to the program manager to get the specific program, and then I type hello world, right? So I do all different things, and it knows intuitively to put this one up in front of the PDF. So it knows when it tells the program when I'm in this specific place here on the screen, don't put the PDF unless the window minimizes or it goes away. If I say save, what's going to happen is it's going to create a file in the SSIDs or RAID, depending on which one your computer is using, so that way when I turn the computer on later, it's saved, right? But if I say don't save, it's not going to update the memory. You see how that works? So the operating system is doing that, and typically, and we'll get more into the concepts of virtual memory. It's typically done, we want to do all of the operations in register and cache. The operating system allocates those. So there's specific memory elements. The kernel, for example, that's used for that. If you want to, forgive me for saying this, but in order to go in more detail, their operating system, that's a whole 2-week script. I don't think you want me to go 2 weeks off on it. Okay, no. Any other questions? Okay. So, what is a block? A block is only, the definition is not the drawing. The minimum amount of data transferred between cache and main memory, right? So in this case, you can see the blue square. I would want to transfer a certain number of blocks between, so I have processor, I have my local registers, right? So what do you think would be a good block size, given what you know about the registers? And exactly right, 32 words, right? Because I want to be able to indicate where the frame starts, where the stack starts, where the what's the specific registers for the save values I would want. If I have a compiler, I know that at some point I need to execute some function. So I'm going to have variables that I wouldn't have passed through the function and know where the function is going to result from. So exactly right. A good block would be 32 words. So then from here, if I'm doing a different portion of the program, I want to be able to swap those out to indicate portions of the program that I'm doing. So I want to have, if I'm using a lot of the same code, like I'm using a function multiple times, or I'm using certain variables a lot, and we know this because of the principle of locality, those are going to end up a lot in my level 1 cache. Level 2 cache, I'm using less often, and we'll say we have level 3 cache as well. Later in the, actually not too far later in the course, I'll be able to demonstrate why having more than 3 levels of cache tends to not be very helpful. All right, so 4 other terms I find students kind of get confused when they're thrown out, but this is going to become very useful. cache hit, hit rate, cache miss, and miss rate, right? So what is a cache hit? I am looking in the cache. Okay, so here's an example. You are my program, you are my local registers. I've done everything that I need to do, right? Or I specifically say, all right, I have I equals j plus k plus l plus n. Well, I only have j plus k plus l here. So I need to find m. So what I'm going to do is, and we're going to discuss how that's calculated using associativity in a moment, I'm going to go to my level 1 cache. And I'm going to calculate where it should be. And I say, are you m? Right? If you are m, or you contain m in your block, that's a cache hit, which we formally define. If the requested data is in the cache, read or write operations are performed directly in cache without accessing main memory. So I say, where's m? Are you m? You have m. I then swap you in, so that way we can complete the operation, right? So that's a cache hit. Your m is supposed to be here. If everything worked out, and you're there. Okay. Hit rate. The probability that the requested memory item is in cache is between 0 and 1. And I presume that you all have taken some probability course. So if you haven't, I saw a couple on those. Basically, 0 to 1 in probability is the same thing as 0% to 100%. So 0.18 means 18%. Cache miss. Hey, you have m. No? All right, now I need to go to level 2. That's a cache miss. Level 2. Are you in? Yes. All right, so that's a level 2 hit. All right. I go here. Are you at? No. Level 2 miss. You're level 3. Are you in? Yes. Level 3 hit. Now if I do the same thing, are you in? Level 3 miss. I now need to go to my main memory and go to my slow disks, right? So then I have to go here. Oh, we got slow. We're in real trouble, guys. Please tell me you guys have M. And then you go, okay, yeah, we have M because we saved it when we turned it off. All right, we need to update everybody. That's a cache miss. So that case we have a level 1 cache miss, a level 2 cache hit, or level 3 cache hit, level 1 and 2 cache miss. Right? It has to work this specific way. Okay? When we get to average memory access time, it's the probabilities that I'm going to find something in the register, plus the probability I'm going to find something in level 1 if I miss there. Or if it's not here, the probability I'm going to find it in level 2. If I don't find it there, the probability that I'll find it in 3. And then if that probability that will be in main memory, and in each probability, there's a certain amount of time. So 5 nanoseconds, 12 nanoseconds, 20 nanoseconds, 100 nanoseconds, right? So based on those different probabilities, I'll be able to calculate what's known as average memory access time. And so miss rate is the probability that the requested item is not in memory. So sorry, let me formally define cache miss first. Cache miss, if the requested word is not in cache, a block of words containing the requested word is brought into the cache, and then the processor request is completed. So that would be the case. I go to level 1, I say, are you M? Yes. Okay, well, I need to bring you the cache into the processor. All right, so a good thing to end on would be to discuss this actual average memory access time, which you'll see me refer to as AMAT. And so that's formally defined as, if you have TC is the cache time, the time it takes me to go to the cache and get the information, and TM is the main memory access time. So let's say I have a level 1 cache. So AMAT, this definition here, has 1 level. We'll do this in the example 3.1, and then I'll let you guys find your groups. So my hit rate is H. 95% chance I find level 1 would be 0.95, right? So that's the probability. And let's say that takes 5 nanoseconds. So in this specific case, I'm probably pulling the exact numbers from example 3.1, right? So in 3.1, given a level 1 cache, I only have 1 level of cache, with a hit rate of 95%, a cache access time of 5 nanoseconds, and a memory access time of 100 nanoseconds, find the average memory access time. So the definition from 3.13, my hit rate, H, if I say 95%, the probability is 0.95. So 95% of the time, it's going to take me 5 nanoseconds to get what I need. But 5% of the time, it's going to take me 100 nanoseconds to get what I need. So from here, we use our level 1 equation. My hit rate is 0.95 times 5 nanoseconds, plus the miss rate, which is 1 minus 0.95, which is 0.05, times 105 nanoseconds. So why am I doing that instead of just 100? Because first I need to go, okay, you all have it. It takes you 5 seconds to tell me yes or no. So if it says yes, I'm done. If it's no, if it's a cache miss, I say, you all have it? No. That takes me 5 nanoseconds. Then I need to go to the data to the main memory, which takes me 100 seconds. So that's why in the topical guide objective, TC plus TM is the cache memory time plus the main memory time. So then you perform this calculation, and you see it's 4.75 plus 6.25. Okay, so for the last 5 minutes of lecture, let me go back into Blackboard. I am going to turn